black hole. In the cold, violent depths of the cosmos, a star dies, but its end is only the beginning. What remains is a stellar black hole, typically between 5 and 20 times the mass of our Sun, compressed into a region smaller than a city. These are the most common type, scattered throughout galaxies in enormous numbers. The Milky Way alone may contain hundreds of millions of them. Most are invisible, quietly drifting through space. But some are locked in orbit with a companion star, slowly pulling material off it. That stolen gas heats up as it spirals inward, glowing in X-rays bright enough for our telescopes to detect from thousands of light years away. Supermassive black hole. At the center of nearly every large galaxy sits something almost incomprehensibly massive. Supermassive black holes range from millions to billions of times the mass of the Sun, and they don't form the same way stellar black holes do. Their exact origin is still one of the biggest open questions in astronomy. Some may have grown from the direct collapse of enormous gas clouds in the early universe. Others may have started smaller and merged and fed their way to enormous size over billions of years. The one at the center of our own galaxy, called Sagittarius A star, weighs about 4 million solar masses. In 2019, astronomers captured the first real image of one, the black hole at the heart of a galaxy called M87, surrounded by a glowing ring of heated gas. That image confirmed predictions that had existed only on paper for decades. Intermediate black hole. For a long time, black holes seemed to come in only two sizes. Stellar, which are relatively small, and supermassive, which are enormous. The middle ground was missing, or at least unproven. Intermediate black holes are thought to range from a few hundred to a few 100,000 solar masses. Finding them has been difficult because they don't sit conveniently at the center of galaxies, and they're not always actively feeding. Evidence for them has come from unusual X-ray sources in nearby galaxies, and from gravitational wave signals, where two merging black holes produced an offspring heavier than any stellar black hole should be. They may be the seeds that eventually grew into the supermassive variety, making them a crucial missing link in understanding how the universe's largest structures formed. Primordial black hole. These are hypothetical black holes that would have formed not from dying stars, but from the chaos of the early universe itself. In the first fractions of a second after the Big Bang, matter was distributed unevenly. Regions dense enough could have collapsed directly into black holes before any stars ever existed. Depending on how and when they formed, primordial black holes could range from extraordinarily tiny, even smaller than an atom, all the way up to thousands of solar masses. The reason they attract serious scientific attention is that they are one of the leading candidates for dark matter, the invisible substance that makes up most of the universe's mass. No primordial black hole has been confirmed yet, but ongoing surveys looking for subtle gravitational effects on background light keep narrowing down where they could be hiding. Rotating black hole. Most black holes in nature are expected to spin because the stars and gas clouds that form them already had rotation. A rotating black hole, described mathematically by the Kerr solution to Einstein's equations, behaves differently from a simple non-rotating one. The spin drags space-time itself around with it, in a phenomenon called frame dragging. Near a rapidly spinning black hole, space is not just curved, it is being swept in the direction of rotation, like water circling a drain. There is also a region just outside the event horizon, called the ergosphere, where nothing can remain stationary relative to distant space. Objects that enter this zone are forced to move with the spin. Some physicists have proposed that energy could theoretically be extracted from this rotation, a process known as the Penrose process. Rotating black holes are likely the norm rather than the exception throughout the universe. Charged black hole. In theory, a black hole can carry an electric charge. This type, described by what is called the Reissner-Nordström solution, would form if the collapsing matter had a net electrical charge. In practice, a charged black hole in space would almost immediately attract particles of opposite charge and neutralize itself. The surrounding plasma of ionized gas would see to that very quickly. So while they are mathematically valid solutions to the equations of general relativity, charged black holes are considered more of a theoretical tool than a realistic astrophysical object. They are useful because studying them helps physicists understand the deeper structure of space-time, and they appear frequently in thought experiments and models used to explore the limits of physics near singularities. Micro-black hole. These are the smallest possible black holes, existing at the edge of current physics. They have never been observed, but certain theories suggest they could exist. Some extensions of quantum mechanics and string theory predict that if gravity behaves differently at very small scales, tiny black holes might have been produced in high-energy particle collisions, possibly even in experiments like those at the Large Hadron Collider. They would be unimaginably small, with masses near the Planck scale, and they would evaporate almost instantaneously through a process called Hawking radiation. That process, proposed by Stephen Hawking in 1974, suggests that black holes are not entirely black. They slowly emit radiation due to quantum effects near the event horizon, eventually losing mass and disappearing. For a micro-black hole, this evaporation would happen so fast, it would be gone before it could interact meaningfully with anything around it. Naked singularity, technically not a black hole in the traditional sense, but deeply connected to them. At the center of every black hole lies a singularity, a point where density becomes infinite, and the known laws of physics break down. Normally, this singularity is hidden behind the event horizon, shielded from the rest of the universe. A naked singularity is one where that shield does not exist, leaving the singularity exposed. Roger Penrose proposed what became known as the cosmic censorship conjecture, which suggests that nature does not allow naked singularities to form, that some mechanism always hides them. Whether that conjecture holds universally is still unresolved. Certain mathematical scenarios involving extremely fast spinning or highly charged black holes produce solutions where the event horizon disappears, leaving the singularity bare. Whether this can actually happen in the physical universe, and what it would mean if it did, remains one of the most open questions in theoretical physics.